Good morning, children. This is 12th physics. We are doing chapter number 6, electromagnetic induction. Today we are going to cover the topic that is magnetic energy in an inductor. Now, children, any coil or any solenoid, it can be called as inductor because it has some self-inductance. Now we know what is self-inductance, right? Self-inductance is a property of inductor to oppose the change in the flow of current through it. So now let's see how magnetic energy is stored in an inductor. Now children, suppose here we are having an inductor of self-inductance L, which is connected to a battery of voltage V, and we have connected a key K with it, right? Now initially the key is off. So when the key is off, the current flowing is zero, right? Initially the current that is flowing is zero. Now when we put the key on, the current starts flowing. So it increases from 0 to some maximum value. So as the current is increasing, the magnetic field will increase. That is, magnetic field is denoted by B. So magnetic field will increase, and as the magnetic field is increasing, the flux that is linked with the inductor will increase. And as we know, according to electromagnetic induction principle, if the flux changes in any inductor, then induced EMF or current will be produced in it. And according to the Lenz's law, the direction of this induced EMF will be such that it will oppose the increase in the current. So the induced EMF will be in the direction opposite to the flow of current. We know the current will flow from positive terminal through the circuit to the negative terminal. So the direction of the induced EMF, you can see here, it is in the direction opposite to the flow of current. That is, it is in the direction opposite to the change in current. As the current is changing, it is in direction opposite to that, right? So making it stop from increasing. Now children, here the battery is trying to increase its current from 0 to maximum, but opposite to this, an induced current is produced. So if the battery wants to maintain the current in the circuit, then it has to do some external work, right? Battery has to do some external work, and this external work will be against the EMF because EMF is stopping the current to increase. So this external work will be against the induced EMF, and this external work done by the battery will be stored as magnetic potential energy in the inductor. Now, this magnetic potential energy which is stored in the inductor is equal to the work done by the battery to maintain the current in the circuit. Right, now we know the induced EMF magnitude is E equals to minus L di by dt, where di by dt is the rate of change of current in the inductor. And the voltage V, which is supplied by the battery so that it can maintain the current against the induced EMF, is equal to the induced EMF, that is minus E. Now, as the battery has to do some work in order to maintain the constant current, so let that work be dW. So dW equals to P dt, where P is what? P is the electrical power supplied by the battery. Now we know P equals to VI, right? So instead of P, we are putting V into I. So here, instead of V, we can substitute the value as minus E. So dW equals to minus E into I dt. Now we can substitute the value of E from this equation over here. So it will become minus of minus L di by dt into I dt, where I is the current at some time instant, right? I is the current at some time instant t. Now here if you see dt dt will get cancelled and you are left with minus minus will get cancelled and you are left with L I D I. So this is the small work done. Suppose we want to find out the total work done by the battery in order to bring its current from 0 to capital I. So we have to integrate it. So this will be the total work done by the battery to maintain the current from 0 to capital I. So here we know L is the self-inductance. Its value is constant. So that will come out of the integration. So whose integration we have to carry out? We will carry out the integration of I. So integration of I will be I square by 2. We'll put the upper limit I. It will be I square by 2 minus lower limit is 0. So it will become 0, right children? So here what you will get is half Li square. So this is the work done by the battery to maintain the current from 0 to I. Same will be the magnetic energy stored, magnetic potential energy stored in the inductor. So that is denoted by U. So U is equals to W, which is equals to half Li square. So this is the value of magnetic energy in an inductor. So with this formula, we can calculate the magnetic energy in any inductor.